All right, so this is section 3.1. Oops, what's going on here? And this is verifying identities. So this is something that we'll be doing over the next few weeks. We'll be learning a lot of, we have learned a lot of identities regarding our trig functions. And we'll be learning more even in this week. And every time we learn a new identity, we'll have problems having to do with verifying identities. Okay, so the idea here is we're given maybe some sort of equation. So let me just do this with an example. Cosine squared x, tangent squared x equals sine squared x. We're told that it's true, and we need to confirm that it actually is true. All right. So how do we do that? We use the identities that we already know, manipulate this particular equation here so that we can apply the identities that we already know in order to confirm that this equality right here is actually an equality, right? That it's actually true. All right. So the good news for this type of problem is that it's straightforward in that you know what you need to do, right? You know you need to think about all the identities that you know, and you know you need to use them in order to confirm that this guy here, this statement here, is actually true. The bad news is that there is no real algorithm to these problems. Every problem is going to be different because they perhaps will use different identities. They'll use different manipulations of those identities. They'll use different manipulations of the quantities that you see in the equalities. So it's a general kind of type of problem that you just have to treat every problem as different, as its own problem. But once you get used to them, you kind of get a feel for how to work them. All right, so let's see, for example, how to work this one. So we want to verify this guy. All right. So the another piece of good news is that for our class this semester, we're only going to be doing verify problems. So the equalities that I give you here, or that you'll see in the homework, are all going to be true, for sure true. So you only have to verify that they're true, as opposed to maybe a problem where I give you an identity or equality, something like this, and I ask you, is it true or not? If it is true, then you have to verify it. If it's not true, then you have to explain why. All right. Okay. So how do we verify this? We just think about all the identities that we know, and we manipulate each side of the problem until we can determine whether it's true or not. So the way I like to do these problems, and I highly, highly recommend you do them this way, is, and the way I'm going to be doing it is very useful for other contexts as well. And I'll do an example later on in the lecture of this. But the way I like to do this is, and again, I highly recommend it, is to start out with the identity that they want, like this. And then what we're going to do is we're going to put a question mark here. All right, so the question mark represents the fact that I don't know whether this is true or not. All right, so I'm going to pretend I don't know it's true, and I'm going to manipulate each side of the equation until I can tell whether it's true or not. All right, and what I mean by that is I'm going to, for example, on this left-hand side, use the fact that I know tangent is sine over cosine. And so the tangent squared is sine squared over cosine squared. And so this left-hand side is actually the same as sine squared x over cosine squared x. And so what this ultimately means is that this line up here, our line 1 up here, is equivalent to line 2 down here. Okay. So another way to say it is the question of whether line 1 is true is equivalent to the question of whether line 2 is true. All right. And our goal is always, where every line that we progress, it's easier and easier to tell whether that statement is true or not. Okay. And because every problem as we go down the line is equivalent, right, if we get to a final statement that's obviously true, then that means every statement above it is true. All right. So here we've written tangent in terms of sines and cosines, which is actually one mini technique for this section where something you can always consider is to transform everything into sines and cosines, right? Tangent is sine over cosine, secant is 1 over cosine, cotangent is cosine over sine, etc. Right? So one possible strategy for these problems is to just convert everything to sines and cosines. Why is that? Well, because then you have fewer types of trig functions to have to work with, and so it's easier to recognize whether two things are equal or not. All right. Okay. In any case, the advantage or what we got out of this first step was that we can see the cosine squared and the cosine squared cancel, and so this problem above is the same as asking, so the question of whether cosine squared times sine squared over cos squared is equal to sine squared x is the same as asking, is sine squared x equal to sine squared x? All right. Now this last line is obviously true, right? Oops, sorry, sine squared x. This last line is obviously true, right? So this guy is true. And so therefore, because the problem above it is the same problem, right, just written in a different way, that one is true. And because that one is true, the one above it, which is the same problem except written in a different way, is true. Okay, so in essence, another way you could say it is we verify the last one, right, because it's obviously true. So therefore, the one before that has been verified, and therefore the one before that has been verified. Okay, so our line of reasoning goes up this way and then up to that way. All right, and that's it. That's kind of the idea behind every problem in this section. The differences will be the kinds of identities you might be using and how much manipulation you have to do. For this one, this is our first example. So I did a problem where you only have to do one manipulation and it was very straightforward. But obviously we can have different, more complexity, right? So let's do another one. Verify something like, let's say this, sine cubed x cosecant x equals 1 minus cos cubed x, let's say times secant of negative x. All right, so again, at this moment, we don't know whether this statement is true or not, or we haven't confirmed it, we haven't verified it. And so we write it like this, sine cubed x cosecant x equals with a question mark, right? I don't know whether it's true or not at this current moment. I'm trying to confirm it. And what I want to do is I want to manipulate this expression so that I can tell, right? And in this particular case, we have a lot more complexity. So we're going to work on both sides, right? So for example, I see a cosecant on this left side, and I know cosecant can be written in terms of sine. And so perhaps I might do something like this. Sine cubed x. Cosecant is 1 over sine, so that's a 1 over sine, right? And I know that's going to clean things up because I know the sine cubed will cancel with the sine, so the left-hand side will be simpler than what I had in the previous step. Okay, and let's look at the right-hand side. Again, I can do manipulations on either side or both sides at the same time if I wanted, but always you have to keep in mind that you don't want to change your expression, right? Every line has to be the same, has to be the equivalent problem as the line above, right? So this one here, I can write 1 minus cosine cubed x. I know secant of negative x. Secant is 1 over cosine, so I can write this as 1 over cosine of negative x, right? And I expect that guy is going to maybe do some cancellations as well, right? Because I see a cosine down here and I see a cosine up there. Okay, and again, nothing has changed, right? All I did was I rewrote what the secant meant, and it means 1 over cosine, all right? You cannot change your expression so that it's actually a different equality, so that the problems are not equivalent, all right? Because then you're working on a different problem in essence. All right, so this sign and that sign cancel, so I get sine squared x on the left-hand side, and we're asking, is that equal to? And here, this cosine of negative x, I know cosine is an even function, so I know cosine of negative x is the same as cosine of x. So this is cosine of x, all right? And I know I suspect I want to do this, let's say, because I have a cosine up here, and I know now there's going to be cancellations. Okay, so for a lot of these problems, you don't want to blindly do things if possible. You want to try to do things that you anticipate will give you some benefit, right? So I did this simplification from here to here because I anticipate it's going to help me cancel the cosines above and below, right? I did this first step over here from secant to cosine because I anticipate being able to cancel with the cosines in the near future, 2 steps from now actually, because I see a cosine cubed right there, and I know that secant is related to 1 over a cosine, and so I expect there might be some cancellations. All right, so you might not necessarily know exactly what's going to happen in the future, but you don't want to blindly do something. You want to at least have some motivation for doing whatever you're doing. Okay, so you expect maybe in the future there will be some cancellations, something like that. All right, so now the left-hand side, I'm just going to leave it alone. There's nothing really to do here. On the right-hand side, I can see the cos cubed and the cos cancel. So this is 1 minus cosine squared x. And then finally, I know from the fundamental identity that 1 minus cosine squared is equal to sine squared. So this is just sine squared of x. All right. Okay, by the way, another comment is that everybody will do these problems differently. There's lots of ways to do any of these problems. So there isn't necessarily one concrete way that you have to do them all. All right. For example, for this particular problem, let's just look at even just the last step. I decided to use the fact that 1 minus cos squared is equal to sine squared. But alternatively, I could have said from here, let's say to go to here, I could say throw the cosine squared x to the other side. In other words, add cos squared x on both sides. I'd end up with sine squared x plus cos squared x question mark equals 1, right? And that would be just as good because that's literally the fundamental identity, right? So I know that that's true. Again, you want to get to a point where you know, where that final line is something that you know for a fact is true, okay? So you know this is true, or alternatively, the original way we did it, you know this is true. And so therefore, the line above is true, right? Has been verified. So the line above is true or has been verified. So line above is verified, and so line above is verified. And finally, of course, this last one above, the first one, that's the one that we wanted to verify. All right? Okay. So the rest of this lecture is just going to be doing this over and over again, using perhaps different identities, different features of sines and cosines, or the other trig functions, and so on. And again, every time we learn a new identity, we'll have these kinds of problems where perhaps we need to use those new identities. So as we learn more and more identities, you'll have more and more options in terms of what to use for verification. Okay, so let's do another one. Verify 1 minus cos squared x. I don't need a parentheses there. Sine x equals 1 over cosecant x. All right. Okay, and again, in order to do this, I'm going to start out basically kind of pretending that, or not pretending, but actually literally not knowing whether it's true or not, right? Question mark. Okay, I'm not sure whether it's true, so I'm going to convert it into a different problem that is easier to tell whether it's true or not, and so on. Okay. Again, there's a lot of ways to go here. For example, here I can see the 1 minus cos squared, right? And that's something that you always want to notice. 1 minus sine squared, 1 minus cos squares. you know that that's equal to sine squared, right? Because cosine squared plus sine squared is 1. So 1 minus cosine squared is sine squared, right? So this guy here is sine squared x over sine x, right? And so now our problem is this true? Okay. Let's actually modify the right hand side as well at the same time. Cosecant is 1 over sine, so this is 1 over sine of x. Okay, let's see. So maybe it's too hard to tell, right? This is still pretty messy, so let's simplify it more if we can. Sine squared over sine, that simplifies nicely, right? Is that equal to, okay, 1 over sine. What is that? Well, if we simplify, this is like a quotient over a quotient. This simplifies into just sine of x. All right. So you often are going to need to use facts from algebra, right? So here, depending on how you learned it, one way to kind of explain this last step on the right-hand side is I multiply sine x on the top and sine x on the bottom like that. And then what happens is this sine x cancels with that sine x. So the bottom is just 1. And then the top ends up just being 1 times sine x, which is sine x. Okay. All right, and the question is this one true? This one's obviously true. And so therefore the one above is true, and therefore the one above is true, and we're finished. All right. Okay, another one. So verify 1 minus sine squared x, 1 plus sine squared x is equal to 2 cos squared x minus cos to the 4th x. Verify. All right, so there's a lot of ways we can go for this one. One thing I noticed though is I see a lot of sine squared, cosine 4th, right? So what that means is I can potentially convert everything into just sines or cosines, right? Without having to deal with square roots, which are always a huge pain, right? For example, I know that, again, my fundamental identity says sine squared x plus cos squared x is equal to 1. And so that allows me to convert, right, let's say sines, right? So sine squared x is equal to 1 minus cos squared x. It allows me to convert all my sine squares easily into cosine squares, all right? That's nice because, well, we only have sines and cosines here. So if I convert the sines into cosines, then I'm only going to end up with cosines. And it's going to be much easier to determine whether two sides are the same if they only have the same quantities, right? If the left-hand side only has cosines and the right-hand side only has cosines, it's going to be much easier to tell whether the two sides are equal, right? As opposed to if the left-hand side had sines and cosines and tangents and the right-hand side had secants, cosecants, and stuff like that, it looks a lot more messy. Okay, so again, let's actually use that strategy for this particular problem. Let me write down the problem again. Let's be very disciplined with this. And at this moment in our class, we don't have too many identities. So this section might not be as complicated. But again, as we learn more and more of these, more and more identities, these type of problems potentially could get pretty complex. All right, so just be aware of that. Okay, so we said we're going to try converting all our sines into cosines, right? So we have the question mark there. So 1 minus sine squared, we've already said this a couple times, that's just cos squared, right? And then the 1 plus sine squared becomes 1 plus 1 minus cos squared, right? Because sine squared is 1 minus cos squared. And then let's leave the right-hand side alone for now. Squared x minus cos to the 4th x. Okay. And next step, let's clean up this 1 plus 1 just to make it look a little nicer. So this is 2 minus cos squared x. Is this equal to cos squared x minus cos 4th x? Okay. And then here we can see, well, if I distribute this cosine squared in, I'm going to get 2 cos squared x minus cos to the 4th x. Is that equal to cos, oops, I forgot the 2 up here. 2 cos squared x minus cos to the fourth x. And here, again, we see that this side is literally the same as that side. So this guy is for sure true. And so that's the one above it is true. So the one above that is true. And so finally, the one we actually wanted to confirm is also true. Okay, just a couple more. And you'll be able to try these on your own. Verify. And remember, just keep in mind all the algebra that you know, right? Because there's a lot of algebraic manipulations in a lot of these problems. And so if you're comfortable with that, it'll help you do the problems a lot more. So we want to verify this guy here. This is something, actually, this was from last section, last week. I asked you to actually find the identity that relates cotangent and cosecant. Hopefully you did that. And that would basically have been the same idea as verifying this guy here. All right. But this one here is we're kind of working backwards. We're given the identity and then asked to show that, to make sure it's confirmed that it's true. Last week you would have kind of explored to figure out why this identity was true in a way, or to not to explore whether it's true, to explore in order to figure out what was the identity between cotangent and cosecant. All right. In any case, if I want to verify this, oh, by the way, verifying is always easier than trying to find an identity, because when you verify, you already have the identity in front of you, and you just have to kind of confirm that it works, right? Whereas last week, when I asked you to find the identity, it's not as easy because you're finding something that you don't even know what it looks like. Okay, so this problem should be hopefully easier, and let's take a look. I want to verify, so oops. This is 1 plus cotangent squared x. Is it equal to cosecant squared x, right? So let's transform this into a problem that that's easier. So cotangent, I generally don't like to work with cotangent, so I'm going to write it as 1 over tangent, and 1 over tangent is cosine over sine. All right. Maybe we do that in 2 steps. So cotangent is officially it's 1 over tangent, right? So that's why I'm doing it in 2 steps, tangent squared. And then cosecant is 1 over sine. Okay. All right. Still looks kind of mysterious. So again, maybe we try converting the tangent into sines and cosines. So this is 1 over sine squared x over cos squared x, and the parentheses goes here, question mark, 1 over sine squared x. All right. Okay, now we only have sines and cosines, right? So it's something that we're a lot more comfortable with than having to deal with tangents and cosecants and so on. So even though, the complexity of this third step still looks, pretty high, it still looks like a pretty ugly expression, complicated expression. In a way, I still feel confident that I'm going in the right track, because I'm more confident, I'm more comfortable with this third equation here than I am with the one above, because I'm more comfortable with sines and cosines than tangents. All right, so always keep that in mind. Are you actually progressing, right? Or are you close to progressing, right? Maybe it takes 2 steps to actually progress. Okay, so 1 over sine squared over cosine squared, we can make that into a single quotient. We hate working with quotients on top of quotients because they're really hard to kind of get a grasp of. So it's natural to convert this into this, right? This final expression that I have here is much more approachable than the one above. Okay, so again, I feel like I am progressing because my equality here looks easier, or looks more I'm more comfortable dealing with it. Okay, finally, let's take a look here. Perhaps I can do common denominators on the left-hand side. That would work. But let's take a different point of view. Let's multiply sine squared on both sides. All right, so if I multiply sine squared on the left side, I'm going to have a sine squared hitting the 1 and a sine squared hitting this quotient, but that sine squared is going to cancel with the sine squared down here. right? So I'm just going to end up with, sine squared plus cos squared. Is that equal to, and then sine squared on both sides, of course. I have to do both sides because otherwise my equality would be changing, right? I don't want to change my problem. So equals sine squared over sine squared, which is 1, right? And this one, again, this is my fundamental identity. So I know for a fact this is true. So that means the one above is true. So that means the one above is true. So the one above is true. And so the one I actually wanted to confirm is also true. All right. Okay, so maybe this wasn't perhaps the most efficient way to do this problem, but ultimately it doesn't really matter because I've confirmed it, right? So a lot of times it's easier to do a lot of small steps than to try to do one gigantic complicated step, all right? Okay, so in kind of a mini summary, right, the identities at this point in the class you want to consider are the fundamental identity. We've used that actually quite a few times, right? We used the fact that cosine was even, right, in the previous problem to kind of clear out the negative sign there. We have the sine is odd, right? We didn't use that, but you probably will in the homework. We used, of course, the definitions of tangent, secant, and so on, right? So for those, I'm just going to put dot, dot, dot. We used this one right above, 1 plus cotangent squared x is equal to cosecant squared x, right? We had the one that we talked about last time, tangent squared x plus 1 equals secant squared x, right? And of course, remember both of these, you don't actually have to memorize these because you can always reproduce them from the fundamental identity, all right? So these are some of the identities to keep in mind at this moment when you're doing the problems. And again, we'll be adding to them. Okay, so finally for this lecture, let me give you another kind of application of this idea of using the question marks and to verify something. Okay, so this application, again, there's many circumstances where you can use this idea, but let's ask this. Is 1 plus root 5 bigger than or equal bigger than 3? Right? So this actually comes up quite a bit if you're working with quadratic equations, right? If you have a quadratic equation, you often end up with expression, right? Minus b plus or minus root b squared minus 4ac. And these represent where a parabola hits the x-axis in terms of the picture. And oftentimes you want to know, right, whether these 2 points or exactly where those 2 points are, right? Let's say you want a graph, right? So you want to know, is this point to the right of 2 or is it to the left of 4, something like that, right? So you often want to know whether an inequality is true or not, right? So in terms of what I just talked about, this would be the same as asking, I have 3 here, right? I want to plot the point 1 plus root 5, right? So I'm asking, should 1 plus root 5, should it go here in the picture or should it go here in the picture, right? Which one should it be? Okay, so let's start like this, right? If we're not sure, we just make up a guess. We say, okay, I'm guessing 1 plus root 5 is bigger than 3, and then now I'm going to try to verify it. And if in my last line I get something that's true, right, obviously true, then the answer is yes. If in the last line I get something that's obviously false, then the answer is no. Okay, so here, this is equivalent to, and this is useful because, well, who knows what root 5 is, right? Nobody knows how to calculate these things, or nobody learns how to calculate these things in high school or college or elementary school or anything, right, these days. And so we have to do it kind of in a oblique way, right? We can't do this directly by calculating root 5 by hand, okay? And so we do it with the verification technique, right? Is this bigger than this? Well, that's the same as asking, is root 5 bigger than question mark 2, right? Subtracting 1 on both sides. And if I'm still not sure, I can always do this. I can square both sides. That's the same as asking, is 5 bigger than 2 squared? 4. Now it's very obvious. This one is true, so that one is true, and so that one is true. Okay, so again, this is actually quite useful, right? If I'm not sure let's say 2 root 7 plus 3, how this compares to 9, right? Maybe I just make up a guess, right? Let's guess that this is true, right? And then now we try to verify. Well, again, we don't know, so we should always put a question mark. And then we just change the problem until we can obviously tell, right? So this is the same as 2 root 7. Is this bigger than 6? This is the same as asking. Maybe it's too hard to tell, right? So because of the square root, so let's divide by 2 on both sides. Is this bigger than 3? Maybe I still can't tell, so is squaring both sides to get rid of the square root, right? So that we don't have to worry about having to calculate square roots. This is the same as asking, is 7 bigger than 3 squared? 9? No, right? And so this one, the answer to this question is no. And so the answer to this question is no. And so the answer to this question is no. Okay, so ultimately we realize that 2 root 7 plus 3 is less than 9. All right, and again, this means that especially if you're doing kind of graphs, you know that if 9 is here, you should plot 2 root 7 plus 3 right there, as opposed to on this side. Okay. All right, and one thing I've been emphasizing very heavily is you always put the question marks for all of these. Always put the question marks, because these problems can be long, and it's really easy to kind of forget or lose track of what you're doing from step to step. And if you don't put the question mark, then you might think that these things are equal indeed, right? And then you start to use this as a fact when actually you're trying to confirm whether it's a fact or not, right? So it's always good to keep discipline like that. And of course, also a huge benefit is that when you come back to your work in order to study for the exams, which is, by the way, this week, you can read your past work, and so it'll help you study, right? If everything is a mess and you don't know, you couldn't really understand or read what you were trying to do, it makes it a lot harder to